Okay, let's just get right to a hard truth that nobody in the AI space really wants to admit in this explainer. Python agents? Yeah, they are absolutely fantastic for whipping up a cool demo on a Tuesday afternoon. But in production, they absolutely die. I mean, try scaling them for continuous 24/7 business workloads and watch them just hemorrhage memory, drop transactions, and literally bleed your money.
So why does this happen? To understand it, we actually have to look way past the code itself and focus on a concept that I call agentic economics. We have to see how deep-rooted technical debt in your software architecture is directly attacking your company's bottom line. When you move from a prototype to a system that runs 24/7, making autonomous decisions, all those tiny little inefficiencies, they compound into massive financial liability.
$12,000. That is the exact amount our case study fintech company, we're going to call them Ledgerflow, was losing every single month. And the culprit? A mere 120 millisecond Python garbage collection pause. You see, because their agents paused just to clean up memory, two different agents would accidentally race to approve the exact same invoice, causing duplicate payments. 12 grand a month, literally evaporating, all because of a background software process.
Let's dive a bit deeper into this in Section 1, Python Agents Die in Prod.
So Ledgerflow is dealing with a massive 50,000 invoices per day processed entirely by a 24/7 background AI agent swarm. But their old Python stack was completely choking. They needed 20 large EC2 servers just to handle 10,000 parallel tool calls. And I'm using the word parallel with massive air quotes here because they were totally bottlenecked by Python's global interpreter lock, which only lets one thread execute bytecode at a time. This fake parallelism caused memory leaks of 200 megabytes an hour per worker. That forced restarts every 6 hours and just completely dropped 3% of all their transactions.
Which brings us perfectly to Section 2, how GC bleeds your P&L.
This right here is the absolute core of agentic economics, where engineering flaws just directly smash your bottom line. Because Python's GIL prevents true concurrency, you're forced to pay for excess bloated servers. Because of garbage collection pauses, you suffer system downtime, dropped transactions, and those duplicate invoice payments we talked about. And because Python lacks strict compile-time type safety, a simple variable error can slip right through to runtime, resulting in a $10,000 wrong payment to a vendor.
So how do we fix it? Let's check out Section 3, Old Stack versus New Stack.
To stop this massive financial bleeding, Ledgerflow made a really radical decision. They threw out the bloated Python snake entirely and rebuilt their agent runtime from scratch in Rust. By utilizing the Tokyo async runtime, they can now handle 10,000 true parallel tasks on a single machine without any blocking. They adopted the RIG framework to ensure type-safe tools and structured output. And honestly, the best part? A totally clean system design that deploys as a single 18 megabyte binary. Zero Docker overhead, zero Python environment hell, just one clean binary.
The infrastructure footprint reduction was absolutely dramatic. I mean, they went from 20 servers down to just 2. And because Rust doesn't use a traditional garbage collector and manages memory safely on its own, they gained a system that runs for 30 days straight with zero memory leaks and zero garbage collection pauses. This is true Tokyo parallelism that actually works at scale.
Let's look under the hood in Section 4, Type Safe Deep Dive.
I really want to show you how Rust's strict typing system actively prevents those horribly expensive business logic errors. At the center of Ledgerflow's transformation is the RIG framework. Out of all the Rust options out there, RIG is for sure the business-ready framework that is just perfect for production finance agents. Why? Well, it enforces strict type safety right out of the box, provides macro-generated tool schemas, and unifies routing across more than 20 different large language model providers. Think about it like this. When you define an action, like approving an invoice, the amount is strictly defined as an F64, which is a floating point number. If an intern accidentally modifies the code and passes a string, like typing the word 10,000 instead of the actual number, the Rust compiler violently rejects it before the code can even be built. In Python, that type of error might only show up at runtime, way after you've already authorized a disastrous financial transaction. Now, to be fair, there are other great tools in the Rust ecosystem. Integrata is fantastic for nested sub-agents and really complex custom memory layers. Axon-REI is incredible if you need to ship a tiny binary to edge systems or point-of-sale devices. And ADK-Rust is a super lightweight option for local routing. But when you're building cloud-based, P&L-driven agent workflows, where structured output is absolutely non-negotiable, RIG is the ultimate choice.
Okay, moving on to Section 5, the P&L impact math. This right here is the viral money shot of this entire architecture shift. This is not just tech hype, guys. By switching to Rust and Rig, Ledgerflow dropped their server count by a massive 90%. Their infrastructure costs plummeted from $3,800 a month down to just $380. Average latency dropped by 83%. And most importantly, that error rate, the one causing all those duplicate payments, dropped from 3.1% to 0.08%. That virtually eliminated their $12,000 a month reconciliation bill overnight.
When you look at the raw infrastructure savings side by side, it's undeniable. Migrating your agentic systems to Rust isn't just some fun engineering upgrade to keep your developers happy. It is a massive EBITDA driver for your entire business. You are literally doing more work, infinitely faster, for a tiny fraction of the operating cost.
So let's wrap this up with Section 6, 4 steps to migrate.
If you want to stop your own P&L from bleeding out, you can literally steal this exact operational framework. I call it the 4D Rust migration. Step 1. Deconstruct your Python bottlenecks to find out exactly where the GIL and garbage collector are costing you time. Step 2. Delegate those concurrent operations to Tokyo tasks for true parallel execution. Step 3. Decide on strict type safety with Rig to eliminate those brutal runtime errors. And Step 4. Document and deploy your system as a single, lightweight binary. Follow this, and you can absolutely recreate Ledgerflow's success for yourself.
And that brings me to the final question I really want to leave you with in this explainer. Take a hard, honest look at your agent architecture right now. Are you paying for an expensive, bloated demo that leaks money every single hour? Or are you finally ready to graduate from Python, embrace type safety, and build a production system that truly scales? The numbers are crystal clear. The choice is yours. Thanks so much for joining me, and I'll catch you in the next one.